I'm Mercurides, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 24. Find the millionth permutation in lexicographic order of the digits 0 through 9. A permutation is just a fancy mathematical word for a chosen ordering. As shown in the problem description, the permutations of the digits 0, 1, and 2 are 0, 1, 2, 0, 2, 1, 1, 0, 2, 1, 2, 0, 2, 0, 1, and 2, 1, 0. The phrase lexicographic order more or less means dictionary order. So all of the permutations which start with 0 come before those which start with a 1, and so on. When two permutations have the same first digit, we use the second digit as a tiebreaker, and the third digit if needed after that. This is exactly the same technique we use to sort English words in the dictionary, just applied to numbers instead of letters. We've seen all the permutations of 0, 1, and 2 listed out. Let's do the same for 4 digits, 0, 1, 2, and 3. We'll list them out in lexicographic order once again. We get 0, 1, 2, 3, 0, 1, 3, 2, 0, 2, 1, 3, 0, 2, 3, 1, 0, 3, 1, 2, and 0, 3, 2, 1. That's all of the permutations that start with 0. Then we get 1, 0, 2, 3, 1, 0, 3, 2, 1, 2, 0, 3, 1, 2, 3, 0, 1, 3, 0, 2, and 1, 3, 2, 0. For the 2s, we get 2, 0, 1, 3, 2, 0, 3, 1, 2, 1, 0, 3, 2, 1, 3, 0, 2, 3, 0, 1, and 2, 3, 1, 0. And finally, the 3s give us 3, 0, 1, 2, 3, 0, 2, 1, 3, 1, 0, 2, 3, 1, 2, 0, 3, 2, 0, 1, and at last 3, 2, 1, 0 in descending order. When we had 3 digits, the number of permutations was 6, as we saw in the problem description. Now, when we have 4 digits, the number of permutations is 24 in all. Going in the other direction, there's clearly only 2 possible permutations of 2 digits, 0, 1, and 1, 0. And with just 1 digit, the only permutation is, of course, the digit itself. If you've been watching this series for any amount of time, this sequence of numbers should look very familiar to you. In general, the number of permutations of n digits is n factorial. So if we had 5 digits, the number of permutations is 5 factorial, or 120. 6 digits gives us 720 permutations, and so on. The reason for this is relatively straightforward once you draw it out. Suppose we want to calculate how many permutations there are for 6 digits. Combinatorially, we need to ask ourselves a few questions. To come up with a permutation, we need to place the 6 digits in 6 positions. How many choices are there for the very first slot? Well, we have 6 digits, so the answer is clearly 6. Next, how many choices are there for the second slot? The answer isn't 6 because we just spent a digit in the first slot, and a permutation never repeats values. The exact digit we use doesn't matter right now. All that matters is that one of these 6 digits has been used. There are 5 digits left, so we've got 5 options. For the third slot, we have 4 options, since we've used 2 digits so far. For the fourth slot, we have 3 options. For the fifth slot, we have 2 options. And finally, for the sixth slot, we only have 1 option, our final remaining digit that hasn't been picked yet. That's 6 times 5 times 4 times 3 times 2 times 1, or 6 factorial, ways we can possibly construct a permutation of these digits. The problem asks us to look at 10-digit permutations, of which there are 10 factorial, or 3,628,800. Our task is to find the millionth one. We can solve this in Python, frankly, with rather comical ease. Every function we need for this is built into Python. All we have to do is import the Iterators standard library package. Iterators is Python's version of Ruby's enumerable or Elixir's enum. It gives us all of the higher-order streaming conveniences that functional programmers have come to expect. One of those conveniences is called permutations, and it does exactly what it sounds like. The permutations function produces all of the possible permutations of its input as an iterable object. All of the functions in Iterators, including permutations, are lazy by design. So even though there are 3,628,800 permutations, simply invoking this function on a sequence of 10 elements doesn't construct a 3 million element list. In fact, it doesn't calculate any permutations at all up front. It simply sets up the computation so that it can be performed lazily when we need it. Once we've done that, we ask for the millionth element. We can't simply access it with brackets, since what we have is a lazy iterable object rather than a list. But we can use another function from Iterators called islice to extract the piece of the iterable we want. This returns a new iterable which contains a subsection of the original. Then we call next to get the next, and in this case only, element of the islice iterable and print it out. And we're done. This solves Project Euler problem number 24 in Python. Tune in next time when we solve problem number 25 in Malbolge. I don't know about you, but that's just not satisfying. We didn't really solve anything per se, we just glued together a few existing solutions and happened to get our number. Let's zoom in for a minute and actually write a function that generates these permutations ourselves. There are lots of convenient algorithms for generating permutations. The one we'll be using today is attributed to Narayana Pandita, and it's guaranteed to give us all permutations in lexicographic order. We'll start with our so-called minimal permutation. That's all of the digits we're interested in, written in ascending order. This is clearly the first permutation. We store this in a list, and we'll run an algorithm iteratively on that list, mutating it in place as we do so. I'm going to describe this find next permutation algorithm in words quickly, and then I'll show you how it works in practice. First, we look for a pivot. Starting from the back of the list, find the first element which is strictly greater than its following element. Call this element the pivot. If no pivot exists, then the list is monotonically decreasing, which means we're on the last permutation and we're done iterating. Once we have the pivot, start searching from the back of the list again. This time we're looking for the first element which is strictly greater than the pivot. Such an element must exist since the pivot was defined so that its following element was greater. Call the first such element the pivot's successor. Now swap the pivot and the successor. Finally, take the entire sublist, starting just after the pivot and going to the end of the list, and reverse it. We've just found the next permutation. That was a lot to take in. Let's see how and why it works in practice. Suppose our current permutation is 0, 1, 2, 3, 6, 7, 9, 8, 5, 4. We want the next permutation. First, we find our pivot. It's not 4, since 4 is the last element of the list. It's not 5, since 5 is greater than 4. Likewise, 8 is greater than 5 and 9 is greater than 8. But 7 is strictly less than 9, so 7 is our pivot. So what makes the pivot special? We want to produce a permutation that's larger under the lexicographic ordering. The pivot is the first element that we can benefit from swapping further to the right. Looking at the 8 again, it does us no good to move the 8 further to the right, since we would be pulling a 5 or a 4 to the left. The left digits are more significant in lexicographic order, so moving a smaller number to the left and a larger number to the right just makes our permutation smaller, which is the opposite of what we want to do. On the other hand, swapping the 7 to the right might help us, because it might move a larger number to the left. Now we find our successor. The successor is the rightmost value greater than our pivot. 4 is less than our pivot, so is 5, hence 8 is our successor. The successor is the ideal value to swap with the pivot. It's useless to swap the 5 or the 4 in for the same reasons discussed when finding our pivot. Swapping a 7 with the 5 or the 4 would just make our permutation smaller. And given the choice between the 8 and the 9, we choose the 8 since we want the very next permutation, and 8 is smaller than 9, so it'll produce a smaller permutation. Now we swap the successor and the pivot. We get 0, 1, 2, 3, 6, 8, 9, 7, 5, 4. At this point, we've committed to starting our permutation with 0, 1, 2, 3, 6, 8. Furthermore, this will be the smallest possible permutation that starts with that sequence, since the previous permutation started with 0, 1, 2, 3, 6, 7. And if this is going to be the smallest possible permutation with that prefix, then everything after the designated prefix should be in increasing order. But it's in decreasing order right now, based on our algorithm to find the pivot, which is why we reverse everything after the pivot. And that gives us our next permutation. Great! Now pause this video and do that 1,000,000 times on a whiteboard to get the solution to this Project Euler problem. It'll probably take you a year or two.
2,000 years later.
Now that you've done that, let's write a C++ program that can do it in under a second. First, let's write a function that takes an array and finds the pivot by counting backwards from the end. Iterate starting at the length of the array minus 2. At each position, check if we're less than the following element. If so, return the current position as our pivot. If we reach the end without finding a pivot, return nothing, as there is no next permutation. There are a couple of things to note here. First, if you're a Java programmer, you may have been expecting me to write t followed by square brackets to designate the array type. Indeed, Java and many other languages borrowed their array syntax from C++, which in turn borrowed its original array syntax from C. However, those C-style arrays have a few problems in C++, largely owing to their compatibility with C. C-style arrays don't know their own size, and they eagerly decay to pointers when used as arguments, which results in counterintuitive argument passing semantics. The standard library type stdarray is equivalent in performance to a C-style array of compile-time known size, but it behaves like a typical C++ class, knows its own size, and acts like other classes when it comes to argument passing semantics. All in all, stdarray is a safer C++ alternative to old C-style arrays. Second, stdoptional is C++'s optional type. This should be very familiar to Haskell or Rust programmers. For any type t, an optional t either contains a t, or is the special designated value called nullop. But pointers do the same thing, right? A t star either points to a t or is the null pointer. In modern C++, we generally try to avoid messing with raw pointers for this exact reason. A lot of legacy code is written with implicitly non-nullable pointers. A t star might be nullable, but there might be an implicit contract on the function that demands it be non-nullable. The type itself doesn't tell us anything about whether or not it should be nullable. Optional t, on the other hand, is very clearly a nullable value. It might or might not exist. If it shouldn't be null, then I would have returned a t, rather than going way out of my way to return an optional value. With that out of the way, we write our find successor function. Given the position of the pivot, this function counts from the back and finds the first successor of that pivot, returning its index. We return a number, not an optional value, since the successor is guaranteed to exist according to our algorithm. We should never escape the for loop without returning, but if we do, throw an exception since something has gone horribly wrong. Now we have the two pieces of our puzzle. Let's put them together. We write a function, find next permutation. This function takes a reference to an array and mutates it in place to become the next permutation. Additionally, we return a boolean indicating whether or not we found a next permutation. We won't actually use this boolean in this sample program, but it makes sense to communicate that value back to the caller in principle. First, we find the pivot. The keyword auto tells C++ to infer the type of the variable, which in this case is optional of size t. Optional values can coerce to boolean and are considered truthy if they contain a value and falsy if they're the special sentinel value null-opt. If our pivot is null-opt, return false and do not modify the input array, because we're done. Otherwise, find the successor. Next, swap the successor in the pivot. Finally, reverse the tail of the array and return true since we found a permutation successfully. Now inside main, we initialize our array of 10 digits, then we find the next permutation, 999,999 times. Since we started with the first permutation, this will give us the millionth. Finally, print out the permutation and exit the program. This runs instantaneously and gives us the correct result. But as ever, I have a few notes. Well, just one note actually. This algorithm, as written, is special case to work specifically on arrays. The arrays can contain any type, as long as that type can be ordered with the built-in greater than and less than operators, but we can still only pass the built-in type stdarray from the C++ standard library. We can't pass vectors or decks or any other home-baked container type. To abstract this algorithm, we'll need to talk about how iterators and ranges work in C++. But first, we're going to rewrite our current array-centric code to be more conducive to iterators. C++ iterators generally like to start at the beginning of a container and iterate forward, but every step of our current algorithm starts at the back and iterates in reverse. We look for the pivot starting from the end, we find the successor starting from the end, and we reverse a tail of the list starting past the pivot and going to the end. This isn't strictly speaking a limitation, but it would make the resulting iterator code more complex than it needs to be. So let's rewrite this code to work from the front rather than the back. We'll start from the permutation 98765432210, and we'll do all of our searching and modifications from the front. Then, at the very end, we'll simply print out the final result in reverse. Our find pivot function starts at 1 and goes to the end of the list, rather than starting at the end and going backwards. We compare our potential pivot with the previous element rather than the next one. Then, in find successor, we iterate from the front rather than the back as well. Our reverse operation, rather than going from just past the pivot to the end, goes from the beginning up to and excluding the pivot. In main, we initialize our array in reverse order, since we're doing the whole computation from the front rather than the back. And finally, we insert another reverse call at the end, this time for the whole array, so that we print out the result in the reverse, or correct, order. With all of that out of the way, let's talk about iterators. C++ has one of the most mature iterator hierarchies I'm aware of. Most programming languages define a basic iterator type. This iterator starts at the beginning of a container and moves forward when requested, stopping only when it hits the end of the container. Some languages add a few optional pieces of functionality on top of this. For instance, Java iterators can optionally support a remove operation to eliminate elements from the sequence while iterating, and C# enumerators can leap back to the beginning of the container with the reset method. But the core functionality is still the same. A few languages even provide richer iterators for certain containers. For instance, Rust iterators can be double-ended, which allows users to pull elements from the front and the back of the underlying sequence simultaneously. C++ iterators are organized into a hierarchy of no less than 5 distinct interfaces, or concepts in C++ terminology. We'll only require the most basic few iterator concepts in our particular case, but I'll go through them all quickly nonetheless. The most basic type of iterator is an input iterator, which is more or less what many other languages such as Python consider an iterator. An input iterator can have its current value read with the prefix star and can be incremented with the prefix ++. Note that input iterators are, generally speaking, single pass. So once you've advanced, you can't go back and look at previous elements, even if you still have a copy of the iterator from before the advancement. An output iterator is the same thing but for output. Whereas input iterators can be read with the prefix star, output iterators can be written to with the prefix star. Like in the case of input iterators, output iterators are generally single pass in the abstract. Forward iterators refine the concept of an input iterator by requiring that the iterator be multi-pass. Suppose I have an iterator called I, then suppose I make a copy of that iterator called j, and then I increment I with ++i. If I and j are only input iterators, then incrementing I invalidates j. I'm no longer allowed to look at the contents of j once I has been incremented. However, if we're dealing with a forward iterator, then j remains a valid iterator to the element immediately before the one that I now points to. A bidirectional iterator is a forward iterator that can also be decremented. Bidirectional iterators are required to support a prefix ---- operation, which takes us back to the previous element of the underlying container. Naturally, ++ and ---- must be inverses of each other on their respective domains. Finally, a random access iterator is a bidirectional iterator that can also be advanced in constant time by any amount with plus equals or minus equals. Most standard library containers provide random access iterators, since most standard library containers can provide random access to their contents in constant time. C++ iterators are typically passed as a pair of values. The first indicates the start of the iteration range, and the second represents one past the end of the range. We've already seen an example of this with std reverse, which takes both the beginning and the end of the range to reverse, with the end being an exclusive upper bound. However, as of C++20, the language provides an abstraction called a range, which can be thought of roughly as a pair of iterators smushed together into one aggregate data type. Specifically, a type is considered a range if there are member or standalone functions called begin and end, which accept the type as their argument. This may seem like a relatively basic abstraction, but it gives us a lot of power. Now we can easily write functions that work on arbitrary containers, taking a container and returning an abstract view object of the results as a range. This makes lazy algorithms, as well as algorithms that might produce infinite iterators, much easier to implement. On top of the base concept of range, C++ defines parallels for ranges whose underlying iterator satisfies certain requirements. An input range is a range whose underlying iterator is an input iterator. Output, forward, bidirectional, and random access ranges are defined analogously. Let's see how to use ranges in practice. First of all, the new range functionality is in the std ranges namespace, which I abbreviate to simply ranges here for brevity's sake. Now, let's write findPivot. We take a forwarding reference to an input range, and we'll return an optional iterator, where the type of the iterator is determined by the range type R. Start iterating at the beginning, and go until we hit the end. As we iterate, keep track of the last element we've seen for the sake of comparison. If we find a match, just return the iterator pointing to the match. Again, implicit conversion rules take this from the iterator type to an optional type containing it without our intervention. If we reach the end of iteration without finding a match, return nulloc. Find successor is actually really convenient once we're using the functions from the ranges header, as one of those functions is findIf, which returns the first element matching a predicate, and that's exactly what we want to do. So we can write the entire findSuccessor function in just one line. Well, plus 3 lines for the type signature and concept constraints. Finally, findNext permutation takes a forward range rather than an input range, since we'll be iterating over it multiple times. But otherwise, this function looks about like it did before, with the exception that we get the starting iterator with ranges begin rather than a member function. Main looks pretty much identical to before. One thing of note is that rather than reversing the array in place, we can call ranges reverse view to get a view of the array backwards without actually modifying anything. Now we have a much more abstract program, and we've learned a thing or two about C++ iterators in the process. But we can actually do even better. Our current solution iterates blindly a million times and then prints out the result, but we can actually find our answer without generating any other permutations. Let's make a counting argument to see why that is. Let's go back and look at the permutations of just 4 digits again. There were a total of 4 factorial, or 24 permutations, and here they are listed out in order. Note that, obviously, all of the permutations starting with a 0 come first. How many such permutations are there? If we fix a 0 in the first slot, then we have 3 digits to place in 3 slots, so there are 3 factorial, or 6 such permutations. If I'm looking for the 10th permutation of 4 digits, I can safely skip over all of the permutations that start with 0, knowing that I've skipped exactly 6 permutations. Now, I just have 4 permutations left to go. We can even apply this principle recursively. Once we know the first digit using this technique, we can apply the same trick to the remaining digits to identify them. Doing so, we can actually build up the correct permutation using just factorials without ever generating any of the permutations that come before. I would show you a small example of this, but frankly, we can just jump right in and solve this Project Euler problem by hand. We want the millionth permutation, and to start with, we know nothing about our answer. Our remaining count starts at 1 million, and we can never let that number hit 0 or below. If we do, we've gone too far. First question, is the first digit 0? There are 9 factorial permutations where the first digit is 0. 9 factorial is 362,880, which is not big enough. So we can skip over all of those permutations that start with a 0 and subtract 362,880 from our count of a million, getting a new remaining count of 637,120. Now, is the first digit 1? Again, there's 362,880 ways this could happen, but we still have over 600,000 permutations to go. So the answer is no, and we cancel off another 9 factorial solutions. Now, is the first digit 2? Again, there are 9 factorial, or 362,880 ways this can happen, but we only have 274,240 permutations to go. So the answer in this case is yes, the first digit must be 2. Now we start trying to identify the second digit. After fixing the second digit, there will be 8 slots left, so this time we'll be subtracting 8 factorial, or 40,320 each time. Is the second digit 0? No, our remaining count is at least 40,320. Subtract 40,320 from our count and move on. Is the second digit 1? No, remaining count is still at least 40,320, so keep going. The second digit can't be 2 since we already used 2. So try 3, then 4, then 5, then 6. None of these work, so we just keep subtracting. At this point, the remaining digit count is 32,320, and 8 factorial is 40,320. So the next digit, 7, must work. The number starts with 2, 7. Now we're working with 7 factorial, or 5,040, for the third slot. And our current remaining count is 32,320. We try the number 0, then 1, then 3, 4, 5, 6. I'm going quickly, but all we're doing is subtracting 7 factorial every time I fail to put a number in the slot. Finally, when our remaining count is 2,080, and the digit we're trying to insert is 8, we get to the point where we insert the next digit, since 7 factorial, or 5,040, is bigger than our remaining count. Working quickly now because we have the basic idea. We're looking at 6 factorial, or 720. We'll fail with 0 and 1, but succeed with 3, so the next digit is 3. For the fifth digit, we're looking at 5 factorial, or 120. We fail at 0, then 1, then 4, 5, and 6, so it must be a 9 by process of elimination. Now our number of possibilities is 4 factorial, or 24. 40 is greater than or equal to 24, so the next digit is not 0. But it is 1, since 16 is less than 24. Now we want to subtract 3 factorial, or 6. We can't put a 0 here, or a 4, but we can put a 5 here, and the remaining count is now 4. The next factorial is 2 factorial, or 2. We can't put a 0 here, and our remaining count becomes 2. Now the next option is 4. Can we put a 4 here? Actually, we have to. In order to skip over 4, we'd have to subtract 2 from our remaining count, and I said the remaining count must never hit 0, so the next digit is 4. At this point, the problem is trivial. We're looking at 1 factorial, and the possible digits are 0 and 6. Skip over the 0, but place a 6. And then the final digit must be 0 by process of elimination. And there you have it. No computers necessary. But this is a programming web series, so let's write some code. Let's do everything we just did in C++. First, we write a quick factorial function. The largest factorial we'll need is 10 factorial, or a little under 4 million, so it'll fit easily into a standard C++ integer. Now for our main code. We start with a vector of all 9 digits in ascending order, as well as an initially empty solution vector. Our remaining count is 1 million. We iterate 9 times, 1 for each slot we want to put a digit in. We actually have 10 digits to place, but the 10th one will clearly be whatever's left over after placing the first 9, so we don't need a loop iteration for that one. Inside the loop, calculate the current number to subtract as the factorial of all but one of the remaining digits. Then try each digit in turn. For each digit, if the new remaining count is greater than 0, skip over that digit and decrease the remaining count by a commensurate amount. If not, insert the remaining digit, remove it from the digit candidate list, and break the inner loop. At the end, push the sole remaining digit to the solutions vector and print out the digits in that order. This gives us our solution without allocating any intermediate permutations, and this is the approach we'll use in our final solution for today. Today we'll be working in C shell, or more precisely, we'll be working in its improved variant, TC shell. A couple of years ago, we used Windows Bash to solve a Project Euler problem. TC shell would be the first Unix shell we use, though it certainly won't be the last. Whereas Bash is designed to automate the task of Windows command line scripting, a Unix shell, such as TC shell, is designed to automate the same on Linux and Unix-like operating systems. C shell in particular borrows some of its syntax from the C programming language, while still retaining all of the usual semantics of a POSIX-compliant shell. Most things work like you'd expect if you've ever used Bash or any POSIX shell, with some slight syntax differences. Variable assignment is preceded by the set keyword. Like Bash in many shell languages, TC shell treats everything like a string and converts to a number on the fly when needed for arithmetic operations. So the right-hand side of the set command is treated as a literal string or list of strings. On the other hand, if we want to do arithmetic, we can instead use the @ command, whose right-hand side is an expression rather than a list of strings. This expression syntax supports all of the usual arithmetic operations such as plus and minus, as well as comparisons, Boolean operators, and a few file existence checks thrown in there just for good measure. The most common POSIX shell, Bash, tends to end blocks with the reverse of the word that started them. So if statements end with the word fee, case blocks end with asac, and so on. C shell went with a more conventional block ending syntax. Most blocks, such as while and for each loops, end with the keyword end. If statements end with the single token and if. Like in other POSIX shells, we can delegate to a subshell with backticks and capture the output, and a single vertical bar can be used to pipe the output of one command into another. We don't need a whole lot of firepower for today's Project Euler problem, but there is one little issue. We did write one small helper function called factorial. C shell actually doesn't have a way to write functions in a script file, unlike the Bash shell. We can write aliases, which delegate to a one-line command, and I'm sure if we really tried, we could squeeze our factorial function down to one line. Or we could put the factorial function in a separate file and call it just like any other command. But I have a simpler solution. We know in advance that we'll only ever need the factorials from 1 to 9, so let's just pre-compute them. Here's a string containing all 9 factorials we'll need, separated by whitespace. When we need a factorial, we'll do a bit of clever text manipulation to pull out the part we care about. With that in mind, let's jump right in and write our solution. Remember that we're using our counting solution, which zooms in on the correct permutation without having to iterate a million times to get there. We start with a remaining count of 1 million. Our string of valid remaining digits starts out as all of the digits from 0 to 9, and the result string starts out, well, empty. Loop 9 times. For each iterates over a list of strings. In this case, the strings representing the numbers from 1 to 9, and binds the variable to the respective value for each loop iteration. In our case, we don't really need the variable, as we just want to loop 9 times in the abstract, so we won't end up using the variable do times. Inside the loop, we get the remaining number of digits. To do this, we pipe the value of the nums variable to the wc word count utility. When given a -c option, wc returns the character count rather than word count. Next, iterate over the digits we have left. We have a string of these digits, but we want a list, so print them out in a subshell and pipe that output to a grep command that searches for any non-new line character. This search will bear fruit for each digit in our string, so we get a list of digits at the end. Now we want to calculate the factorial of length minus 1. To that end, print out the factorials variable, replacing the spaces with new lines. Now we have a new line separated list of factorials. Do some truncation with head and tail to eliminate the lines we don't want, and we're left with only the factorial we care about. Then calculate new result and check if it's bigger than 0. Like the right-hand side of the @ command, the condition of an if statement is automatically an expression context, so we can directly use comparison and arithmetic operators here, just like we would in C. If we haven't gone far enough, set the remaining count to the new result and start the next loop iteration. If we have, append the current digit to the result. Now we need to remove the used digit from our nums variable. This capability isn't really built in like it was in C++, but we have several good options. In this case, we'll make a new variable called loopVar that keeps track of where we are in our digits list. Then we'll use head and tail again to do some clever arithmetic and remove the digit. Note that head and tail, like wc from before, will operate on characters rather than lines if given the -c option. Finally, if we found our match, break out of the inner loop. At the end of the loops, we concatenate our final digit and print the result. This runs instantaneously and prints out the millionth permutation of 10 digits, without producing any of the intermediate permutations at all, thus solving Project Euler problem number 24 in C shell. Tune in next time when we take a look at problem number 25 in Pete, whose source code is designed to look like abstract art.